Okay, so the second part of this unit is buffers, and it can sometimes give kids a little bit of a, yes, headache. That's good, Daniel. It can give them a headache. So we're going to try to make them as easy as possible, or at least as they're easy as it's going to get. So first of all, what is a buffer? Buffer is a solution that resists small changes in pH. When you have a small amount of acid or base added. If you're adding a giant amount of acid or base, well, obviously you're going to overcome the buffer. Buffers need you can make a buffer two ways: a weak acid and its conjugate base, also known as its salt, or a weak base and its salt. So, for example, HF, hydrofluoric acid, is a weak acid. And so if I had HF and sodium fluoride mixed together, I would be creating a buffer system. Okay? Or I could have a weak base and its salt. So that example of that, of course, would be ammonia and ammonium chloride. Strong acids and strong bases will not make buffers. They like to put that in a multiple choice question, so be careful for that. Okay? Your body is a buffered system. Okay? That's why this is one of my pet peeves when people say, "Oh, you should follow an acidic or an alkali diet because it helps your blood." Whatever. No, your body buffers whatever you put in it to stay the same pH of your blood, and your stomach is made full of stomach acid, so you can't make it basic. So they're lying to you, basically, when they say eat an alkaline diet, eat an acidic diet. Doesn't matter what you're like. Yeah, it's your body's designed to buffer. Okay. Anyway, that's sidebar. If a strong acid is added, the buffer basically reacts to produce a weak acid, and so the pH would only drop very slightly. And then vice versa, if a strong base is added, the acidic part of the buffer reacts to produce water and a weak base. Okay? So buffers cannot contain any strong acids or bases. We already said that. But they can be made if I'm doing a titration with a weak acid and a weak base. They can actually make a buffering system because whenever I add that, it creates its salt. And so you can create one like during a titration, and there's like a buffering region, which we'll get to when we get to acid-base titrations. Okay? And of course, when we're talking about acid-base titration, if it's strong, it's easy peasy, go about your merry way. But you know it's not going to be that. You know it's going to be a weak and a strong, right? So strong acid plus a buffer. The strong acid will react with the base to buffer to produce a weak acid. We already said this, just want to reiterate. Another way to think of this is that the strong acid changes one part of the buffer into the other. In this case, the acetate changes into the acetic acid. Okay? When we're writing these reactions, it's easier to use the H plus to write the reaction rather than the whole acid. So I encourage you to do that instead of writing the whole shebang. Just do H plus. Okay? If I have a strong base plus a buffer, that strong base will react to produce the weak base. And then, of course, when we write that, we want to be using the hydroxide. Okay? So this is just kind of some background stuff before we get into it. What happens if I add more hydrogen or hydroxide than the buffer component? And what happens there is your buffer capacity is exceeded, and then the pH will change dramatically. And when we get to our titrations, we'll see that the pH will go along fairly flat lined, and then all of a sudden it shoots way up, and that's because we just exceeded the capacity of the buffer. And you'll see that when we get to titration curves. How do I make a buffer? I'm glad you asked. Okay. If asked to choose components to make a buffer, look at the pH, look at the Ka, the values, which are going to be values of the weak acids, or Kb for bases. You want to choose a combination that has a pKa value very close to the desired pH of the buffer. What is pKa? Negative log of the Ka, yes. Okay, so that's how you want to approach that. If they're giving you choices and say, hey, how would I make this buffer? Look at their pKa values and match it close to the value that you want for your pH to be. Okay? A couple of background skills. We already know this. It's just a very quick review. We already know that pH is equal to the negative log of the hydrogen concentration, right? We did that already. Ka times Kb is equal to Kw. And then realize that any titration involving a weak acid base is going to be a buffer problem. If I titrate a weak acid with sodium hydroxide, then as soon as that first drop hits into the container, I've made the sodium acetate, which is going to be your weak acid. And so then I've created a buffer. Okay. There are two formulas that can be used to solve these buffer problems. The first one is Henderson-Hasselbalch. It is on the equation sheet, just like that. Of course, A minus is your conjugate, so basically it's your base, and then HA is your acid. Okay? I don't like this formula. I'm going to show you to use a different formula. Okay? That's more direct. But this formula I'm going to show you is not on the equation sheet. So you will have to do what? Memorize it, or okay? This formula is not on the formula chart, but it is an easier way, and I'll show you, because you go directly straight to the hydrogen concentration. We already know if we have the hydrogen concentration, we know how to get to pH, right? Okay, so it's going to take Ka of your concentration of your acid over the concentration of your base, okay? And when you're dealing with the buffer, of course, the weak acid is going to be the acid part, and then whatever your salt is will be the base. Okay, so if you add acid to the buffer, you're simply going to add acid to the numerator. Basically, if I have a buffer system and I add acid, I'm going to have to add some moles of acid and change my concentration. Does that make sense? Because I'm adding acid, right? If I'm adding base, I would subtract some of those out. But remember, when we are adding and subtracting, we need to be in moles, not molarity. So it means we have to take account our volume. If they don't give you a volume, what do you assume? 1 liter, right? Okay. When equal concentration of moles of acid or base are present, this is going to occur at the half equivalence point of the titration. Okay, half equivalence point, which means halfway to the equivalence point, right? This is an important concept, and I can't tell you how many people go into the AP exam and don't know this, and it's like easy points right here. At the half equivalence point, the pH is equal to the pKa. Circle that. I did it in bold, but I really want you to understand that. At the half equivalence point, the pH is equal to the pKa. Okay? So if you are asked to construct a buffer of a specific pH given the table of Kas, again, choose the Ka with the exponent closest to the desired pH, and then use equal concentration of the acid and the base. Now let's work problems. That's more fun. Okay? Says that calculate the pH of a 0.5 liter buffer solution. They told us it was a buffer. That's nice. They don't always tell us. Sometimes we have to recognize it, but they're telling us you got a buffer. That you have 0.4 molar formic acid and 0.7 molar sodium formate before and after adding the 10 milliliters of HCl. So the before is going to be super, whoa, that's a little thick. Okay, so before, I'm going to use my personal favorite equation of buffers, and that is H plus is equal to the Ka over the acid over base concentration. Okay? So, believe in the notes right above the problem, the Ka of formic acid is listed. I forgot to put it in here. 1.8 times 10 to the negative 4. So I'm going to say the hydrogen concentration is equal to 1.8 times 10 to the negative 4. What is my acid concentration? 0.5. What is my base concentration? Well, logically, what does it have to be here? They only gave us two numbers. 0.7. And I know it doesn't say it's a base, but the conjugate, it's the conjugate, or salt is its conjugate base, right? So that's why we're using 0.7 as the base, because that's the conjugate. Sodium formate is the conjugate of formic acid. So we're going to plug that in, and we're going to get our hydrogen concentration is 1.29 times 10 to the negative 4. So then I know how to do pH because I've been taught. So my pH is equal to 3.89. Do you agree and know what I did there before I move on? I just used this equation that I gave you. I could do a rice table there if you wanted. Would you prefer a rice table over that? Okay. Then I will not do a rice table. Okay? Because anytime it's at the beginning, it's a rice table when you have a weak acid or a weak base. Okay? Before I erase this, because I need more room to write, are you good with me erasing it? Yes, Adam has a question, or he's thinking about having a question.
So, on rice tables in this unit, will it always be a 1-1 ratio because we're breaking off one?
Wait, say that again? I just couldn't hear you. It's not that I didn't understand what you said. I literally couldn't hear you.
Will rice tables in this unit always be a 1-to-1? Like, it won't be a 2x?
Oh, that's a very good question. Yes. Yes, because acids always dissociate one hydrogen at a time. And so when you do the second dissociation, you have a new set of concentrations, right? Because you have the concentration of the hydrogen from the first dissociation, but you got to put it in the rice table for the second dissociation. That was a very good question. I'm sure someone else probably had that question. If not, they at least have been enlightened now by Adam.
By you,
Yeah, but see, my assumption is y'all just realized that. I got to make sure I tell you all these things. Okay, so now that's the before. So let's do the after. Okay? So we've added 10 milliliters of acid, right? 10 milliliters of acid. If I do volumes, my pen, I need some new pens. If I do volume times molarity, I get 0.01 moles of H that I'm adding, correct? Do you agree with that? Because that's how much acid I'm adding. So I can still use that same formula I just showed you. I just have to calculate a new concentration of my acid and base, right? Because I'm adding some acid, but I'm also adding some volume. So I'm going to concentrate and calculate the acid. So I'm going to take volume times molarity of the original acid, 0.5 times 0.5, and then I'm going to add 0.01. Because that's how much acid I'm adding to this solution. And then I'm going to divide by the new volume, which is 0.510. That might help if I do that. Okay? And then liters. And then I'm going to calculate that, and I should get 0.51 molar. Are you with me so far? I want to make sure that you know why I did this part right here. That's the amount of acid I'm adding, and I already have acid, so if I'm adding acid, I'm adding more hydrogen to it, right? Does that make sense? Okay. In my equation, acid is my numerator. Okay, so now let's go and do. Right, so now I'm going to calculate my base concentration. So this time I'm going to have 0.5 liters times 0.7 minus 0.01 moles. And then divide by my new volume, which that's going to come out to 0.67 molar. Why did I minus it there? Because what do acids and bases do? They neutralize each other. So the 0.01 acid that I added, it's going to add to the concentration of my H, but it's going to take away from my base because it neutralized it. Okay? So now I have my new concentration, so I can say the H plus equal to Ka, acid over base, so my Ka value did not change, and then we had 0.51 over 0.67, and then that turns out to be, which is my hydrogen, 1.38 times 10 to the negative 4. So I take the negative log of that. Not equal. Got a bracket. So I get my pH is equal to 3.86. So at this point, it's a pretty effective buffer, right? I expect my pH to go down a little bit because I added some acid. So it does go down a little bit, but it doesn't go down by very much. Okay? Before I move on, do you have any questions on what I did? The main thing is I want to make sure that you understand why I subtracted and added on those two things. Okay? All right, let's go to the next one then. The next one says, if you have acetic acid and sodium acetate, what ratio of acid to conjugate base would you need to maintain the pH at 5? Explain how you would make up such a solution. Okay? So if I know my pH, do I know my hydrogen concentration? Say yes. Yes. Thank you. Okay? So if I go, now I'm going to go back to this equation. H plus is equal to Ka, and then acid over base, right? So I've got 1 times 10 to the negative 5th is my acid, my H concentration, because I just calculated that. If you haven't already memorized it just from seeing it so much, can anybody tell me what the K is for acetic acid already? 1.8 times 10 to the negative 5th. I don't make you memorize it, you just do it on accident. Okay? So my acid to base ratio would be 1 to 1.8. Because it comes out to be like 1.8. So basically I would mix 1 mole of acid with 1.8 moles of base. And that's how I would make that buffer. With enough water to dissolve. With enough water to dissolve. Yeah. Mm-hmm.
Did you assume 1 liter? Is that how you could say boil?
Yeah. Yeah. Yeah, if you're not given a volume, always assume 1 liter because it makes our life and math much easier, for sure. Okay. Okay. On to exercise 3. Before I do exercise 3, if you are dazed, lost, confused, this would be where to ask some questions. Or do you think working extra problems helps you understand it? Okay. Then let's go work extra problems. A buffered solution contains 0.25 molar NH3 and 0.4 molar NH4. Calculate the pH of the solution. Okay, so here's the deal. We've got Kb here, right? We've got Kb. So we can't go directly there, right? So we're going to find what Ka is by calculating it. And then we can use our handy-dandy equation. So Ka is going to be equal to Kw over Kb, which is going to be 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5th, which equals 5.6 times 10 to the negative 10. So now solving for our hydrogen, we can plug in the Kb value we just found, the Ka value, excuse me. And then our concentration still acid over base, so it's going to be 0.40 because that's the conjugate, so it's going to act as the acid, and then surely by now you recognize NH3 as a base, which is going to equal 8.9 times 10 to the negative 10 molar. So then pH is going to equal negative log. Which is going to be 9.05. That agrees with us. We know we have a weak base, so at least we know we're in the basic range. If we got a acidic pH and we know we've got a base, we did something wrong. So drop back and punt. Okay. Now calculate the pH when 10 moles of gaseous HCl is added to 1 liter. Okay, so we're adding 10 moles, so we don't have to do the volume times molarity thing, so that's good. What did I say? Oh, yeah, don't add 10. We would exceed our buffer capacity for sure. Okay, so we're going to calculate A again. Right?
Do you have to, I guess, is this just the after, or since we?
We did that before, so now we're saying calculate it after we add 10 moles. That's it, did it again. 0.10. Do what the paper says, not what I'm saying. 0.10 moles of gaseous HCl to 1 liter. Okay? So, again, we're going to do, and they didn't give us a volume up there, did they? So we're going to assume 1 liter. So if we assume 1 liter, so you might want to write that in your problem somewhere, assume 1 liter. So we're going to have 0.40 moles plus 0.10 moles is going to equal 0.5 moles, and then, or 0.5 molarity if we're assuming 1 liter. You good with that? And then I'm totally going to run out of room here. B is going to be 0.25 moles minus 0.1, which is 0.15 moles, assuming 1 liter, 0.15 molarity. So then H plus is going to be Ka, which we already have. .50, 0.15 equals 1.85 times 10 to the negative 9. So then pH equals negative log. So by adding the acid, we lowered our pH a tad and got 8.73. Okay? Again, making sure you understood why this time I didn't do all the concentrations, because they didn't give us a volume, so we just assume a liter to make math in life easier. Okay? And then, let me think. I think this is a good place to stop, because we're going to do titration curves tomorrow. Okay? So let me stop.